Hello everyone, I'm sorry I had to cancel class on Monday. Sure you guys aren't too upset about it. This will be the video that I post on YouTube, and then I'll add the links. I'll probably have to divide it into at least 2 videos just because YouTube doesn't allow me to upload long ones like this. So we are going to be starting a new section. It kind of combines distributed loads and support reactions in a concept called load tracing. Load tracing is specific to construction managers, so you guys in this class tend to pick it up a lot quicker than the other concepts just because it is more relatable to you. I struggle teaching it, so fair warning there. I did want to talk about the quiz though before we started. So after I made the announcement like, hey guys, this is a fixed point problem, I think a lot of you started to change what concept is going on in your head, but I did just want to go over it to make sure that we are all on the same page. The first thing I'm really going to need us to be better about is drawing the correct free body diagrams. I might start awarding more points to free body diagrams that are correct, because even if you can't get the right math on the problem, you could show me what the problem is. Can you diagram this out? Can you put it even into a picture to show me what the problem is? So when I said a fixed point here, and because it's the only support reaction, what I should have gotten is a positive AY, AX, and also AMA. We have to add this in here, okay? When we get our final answer, what we're seeing here so far is just 2 hands that are pulling down on this wrench that's being applied to point A, right? And, dang it. So these loads are coming off like this. That's my arms pulling them. They're not exactly at the Y. My elbows are a little cockeyed, whatever's causing that 60 degree and that fraction format. Okay, but I'm pulling a little bit to the right, a lot to the left, a little bit to the right and to the left, but all of it's coming down. And so that bolt, because it says it's not moving, nothing is working here, this force is not enough to move that bolt, that means that everything is going in the positive AY direction. These 2 forces are creating a clockwise rotation, and so that bolt is holding on to a counterclockwise rotation. It has to be the opposite. It has to be in equilibrium. And so when we see those 2 forces away from A, those lines of actions for B and at C, for BY and CY, those lines of actions weren't passing through A, so they're creating a rotation. Both of them are going clockwise, meaning MA, that moment about A, that couple moment, sitting there is going counterclockwise, counteracting whatever the forces on the wrench are. So I'm just going to do the equations real quick. Forces in the X. I have my guess AX, and then I should have gotten negative 20 plus 15 is equal to 0. And then I got AX minus 5. Okay, and we really enjoyed dropping our units on this quiz, which is fine. We just need to remember that is the very last step. What are we working with? Sum of forces in the Y. Should have gotten negative, and then that's 48, not 78. And 26 is equal to 0. I'm going to add my 74 to the other side, and I get 74 newtons there. Okay, and then when I do my sum of the moments about A, I have to add in that MA. Otherwise, when I do this equation and I don't add my MA, my final answer is going to end up clockwise, which is true. That is the resultant moment, but that's not what's happening at the bolt. What's happening at the bolt is it's counteracting that because it's not moving. It's holding on to all of that force that's being applied on the wrench. So MA, doing this correctly, we should see that it's counterclockwise. If we get negative 48, and that one was 300 millimeters away, and we get 26 newtons times 300 millimeters, all equal to 0. So we see that both are negative, both are creating clockwise rotation, so we're going to get MA is equal to a positive 326,000 newtons times millimeters counterclockwise. It came out positive, so MA has to be counterclockwise because it's counteracting that clockwise rotation that those two arms are putting on the wrench, okay? That's all I'll say about it. That would have gotten you 100% on the quiz. This was the main tricky part, adding that MA when it's a fixed support. We have 3 components, one in the Y, one in the X, and then a moment. Okay, so hopping into today's lecture about load tracing. I think I only have one example problem I'm going to do at the end, but today's just kind of like learning about where these concepts come from. On Wednesday, we'll do more problems associated with them, but what is load tracing? How do I identify it? Where is it taking place? Things like that. So kind of a simple lecture of just learning today. We'll be more doing on Wednesday. So load tracing, load travels along load paths. So when people are designing, engineering, architectural design of buildings, any kind of structures, they're thinking about, okay, when this load is applied, how is it going to get all the way back to the soil and be completely safe? Analyzing those load paths is called load tracing. So when we're talking about resisting loads, we start off with what are our dead loads and our live loads, what's happening, what's going to be the point of this structure, and then how are we going to get it all the way back down. So floor sheathing, bends, joists, transfers the loading to the joists, and then the joists to the top plates, and then the top plates to the studs, and then down to the foundation, down to the soil. So how are we going to get from top to bottom? How are we resisting all of those? The more layers that we are adding, the more complexity that we are designing and analyzing and putting into our system, that just means that the more complex the structure needs to be. It isn't just a house. It is a conference room that will be hosting this many people at different times, and sometimes it'll be vacant and sometimes it'll be fully stocked with people. So how are we designing aesthetic appeal? How does it supposed to look? How are people supposed to see it in every day? Does it need to stand out? Does it need to just sit in the background? What is that complexity of it? So to start, what are live loads and dead loads? Kind of an easy question, but dead loads, the structural pieces that make up the building that kind of sit there. If the building would be torn down, it would be torn down with the building. Live loads, it's the use of the building. So just going to go through a couple of examples. So if we have the weight of the structural beams and joints, would that be a dead load or a live load? Is that part of it or something that's moving in and out? I'm hoping you say dead load. Okay, so weight, structural beams and joists, that's going to be given. That'll be in the design. Vibration from a tsunami. So obviously not in Colorado, but where would the vibration of a tsunami be live load or dead load? How is that impacting? It's not always there. When it does hit, we need to be structurally sound for that, but it would be a live load. Not always there. The vibration, the dampening, all of that would be next. Okay, HVAC system. So that one's a little bit harder when we think of furniture and things being able to move in and out, moving boxes, things like that. HVAC system doesn't really fall into that category. It is made up with the building. So, and it's usually designed around. So that one would be considered a dead load. Next one is snow and wind loads. So a lot of snow or wind loads, snow loads hitting more vertical on a building, wind loads hitting horizontal. Both of those would be live loads, just like the helicopter that lands on top of St. Mary's. Sometimes it's there, sometimes it's not. There's seasons of, we need to be able to design around it, but it's not something that is continuous and that we could control with a specific number all the time. When we're thinking about weight of structural beams and joints, the minute that we design that, we know that that is going to be consistent throughout the course of this building's lifespan. So that's not always the case with wind and snow loads. Okay, So external, okay, what about a party of 50 with an early 2000s playlist specifically featuring Usher? That would, I hope you think of Live Load, okay? People, the use, people coming in and out of are always going to be the live loads of your building or structure, okay? So when we're thinking about structural design, includes educated approximations about dead loads and live loads. So when people are thinking about, okay, here are my cabinets, they're going to be about 10 pounds per square foot, but that's not where it stops. That's not just like, oh, we're just going to throw the studs up and hope that they support 10 pounds per square foot of loading. Of course not. Okay, people have gone ahead and said, you know, in those cabinets, they're going to go ahead and put all their dishes, their KitchenAids, their baking sheets, whatever the case may be. That's increasing the cabinet's load to 40 pounds per square foot. And so that is what we will design our studs for, our wall supports. So it doesn't just stop there. The people that go through the design process really design around dead loads and live loads, even though dead loads at the time of creating the structure, that's the only thing that we have to work off of. But there are approximations that engineers, designers can go off of to make sure that it is suitable.